There are a bunch of vocabulary words that you need to know, and they are on the warm-up that I gave you that day. That was that whole list of words on the one side and the definitions on the other, and you were supposed to mix and match them and then put the letter on the bottom of the page. There's going to be another one like that next week, so I would study that. There are words like chord. It's a line segment that has its end points on the circle. One of the things about a chord that you need to know is that if you find the midpoint of the chord and you then draw a 90-degree angle, right, a perpendicular bisector through that midpoint, this will go through the center of the circle. A chord that is a perpendicular bisector, that little upside down T is perpendicular. Perpendicular bisector of another chord is a radius, a diameter actually, diameter. Okay. Another useful thing to know, if you try to make a tangent line, now tangent line is a line that intersects the circle only once. And if you're working with a radius, in other words, a line segment that goes from the center to the circle, and your line intersects the radius at the circle, then that has to be 90 degrees. And the reason for that is, if it's not 90 degrees, it's going to go through the circle twice. See? So the only way to actually get it to go through the circle once and only once would be to make it be a 90-degree angle. A radius intersects a tangent line at the circle is perpendicular to the tangent. Okay? So if this radius intersects this tangent at the circle, then this has to be a 90-degree angle. Okay, one more thing for this circle, and then there's more than enough here to keep you busy when you're looking at it. You don't want to put too much on the same circle because I don't want it to be too hard to read. Let me extend this tangent line out a bit. If you have two tangent lines, right? I've got one line here that intersects the circle in only one point. I've got one line here that intersects the circle in only one point. Now, they don't necessarily have to intersect because they could be parallel to each other, right? If I had drawn one down here, they would have been parallel. But if they intersect, then the distance from the point of intersection to the point of tangency here, and from the point of intersection to the point of tangency here, are equal. These two segments are congruent. I'm going to call these tangent segments. Right? Going from the point of tangency to the intersection are congruent. Well, although we've mentioned two things here. We've mentioned the angle that these intersect at, and we've mentioned the fact that these two segments here are congruent, and these two segments here are congruent to each other. So let's stick for a moment with the length of segments and which ones are congruent to what and how the measures affect each other. Okay. Moving on to a second circle, I'm just going to draw two chords. One there and one there. Right? Two random chords that intersect. And by intersecting each other, they cut themselves into four different segments. You've got this segment here, this segment here, this segment here, and this segment here. Now, if we take these as the lengths of the segment, A, B, C, and D, it is always true that A times D is equal to B times C. In other words, this length times this length is equal to this length times this length. Okay? So we've got two segments here that intersect inside the circle, right? Two segments that intersect here inside the circle, and two segments here that intersect outside the circle. So we've almost covered everything, except for two things. We haven't covered, I'm going to move all the way over to the right here so I have more room. But if I draw two secant lines, which go through the circle and then continue on, okay. You'll notice that again, we've broken this into segments, right? I've got a segment here that goes from here to here. I've got a segment that goes from here to here. A segment that goes from here to here. Another one that goes from here to here. And then there's the whole segment that goes from here to here and from here to here. So just to do this a couple of different ways, because your book does it one way, right? I'm going to call this A, and this B, and this C, and this D. Okay? From here to here, from here to here, from here to here, and from here to here. But I also want to do one other thing. This length from here all the way to here, right, which would be A plus B, I'm going to call that E, right, the length of the whole thing. Okay? And the same thing here, I've got a length that goes from here all the way to here, and that equals C plus D, and I'm also going to call it F. Okay? So basically what I'm going to do is just sort of trace this in red a little bit to show that the red is what I'm talking about when I talk about E and F. The whole thing. Anytime this happens where you have two secants that intersect outside the circle, the length of the segment from the intersection to the circle times the whole thing of one of them is equal to the segment length from the intersection to the circle times the whole thing of the other one. In other words, in this particular case, B times E is equal to D times F. Now, if you don't have E and F, but you have these two, well, then you can figure out what E and F are by adding them together. Yeah?
If you don't have E and F, would it just be B times B plus A?
Yep. That's why I did this. So E, where I have E here, you could substitute A plus B. And where I have F here, you could substitute C plus D. So moving to this one, the other possible thing that can happen is sort of a combination between this and this. Okay? And that is, I get a secant line here that intersects with a tangent line on the outside of the circle. Now, in this case, too, just like in this case over here, you've got a segment outside and a segment inside for the secant line, but all you have is a segment outside for the tangent line. So if I were looking at the outside segments, they would be A and C. But if I were looking at the whole thing, A plus B here would be equal to D, which would be the length of this whole segment here. Okay. And the length of this whole segment here, well, it's actually just the same. It's C. D stands for A plus B, and it's the distance from here to here. Yes. Sometimes there are numbers, sometimes there'll be variables. The idea here is if we plug in numbers for some of them, you should be able to find the ones we don't plug in numbers for. That's the way this all gets worked out. So in this situation, in a way, it's the same as with this situation. The outside segment of this here times the whole thing, which goes from here to here, is equal to the outside segment here times the whole thing, which is the same. So A times D is equal to C squared. So here is a problem for you to work on. You asked me for an example with numbers, so I've got one here. Okay? The idea here is you're being asked to find the value of t. Right? You have two segments, two chords that intersect. Okay? You're being told that this is congruent to this. You're being told that this is 12 and that this is 3. So, and the question is, can you find t? And the answer is yes, of course you can. Go ahead. Looking at your resource page, the one that you're creating now, this is the picture that looks like what you're trying to solve. You have these two numbers here, and you know that these two numbers are equal to each other, and you're trying to solve that. And so what that said is that this segment times this segment is equal to this segment times this segment. That means 12 times 3 is equal to t times t. 36 is equal to t squared. What number multiplied by itself equals 36? T equals 6.
So you don't just square root it, like...
Well, that is square rooting it. If we square root 36, we get 6.
Yeah.
Yeah. Okay. The only question I want to ask you right now is, what's the value of k? 5. And how do you know that? Because these two are tangents that intersect outside the circle, so the tangent segments are congruent. Okay? K is equal to 5. So take a look at this one. Right? The one I'm going to call number 3. These are two secant lines that intersect outside the circle. You're told that this is equal to 9, this is equal to 6, this is equal to 12, and this whole thing from here to here is equal to z. And you're being asked to find z. Okay, let's take a look at this one. Here's the deal with this. You'll notice that I've added something here. 6 plus 12 is equal to 18. That's the distance from here all the way to here. And what we know from this part of our resource page is that the distance from here to here times the distance from here all the way to here is going to equal the distance from here to here times the distance all the way from here to here. So what does that mean for this one? Well, it means the distance from 6, or this distance here, 6, times 18 is going to equal this distance here, 9, times the whole distance, which is z. Okay? 6 times 18 is equal to 9 times z. Now, before I even multiply 6 times 18 together, I'm looking at this and I'm thinking to myself, I can simplify this. What if I divide both sides of the equation by 9? That would make this one go away, and that would reduce that to 2. So then it would be 6 times 2 is equal to z, and 6 times 2 is 12. So z is equal to 12. Okay. What's that?
How'd you get 6 times 2?
Well, I had 6 times 18 is equal to 9 times z, right?
Yeah.
I wanted to get rid of the 9, so I divided both sides by 9. So let's do this one. Okay. In this problem, you've still got the same kind of thing, two secant lines. You know that 8 out here is the segment here. The whole segment is 21. Here, the segment out here is 9, and this segment in here is A. And you're trying to find A. Okay. So here's the problem that we just did, right? And here's how it works out. Here's what I added, right? I know that from here to here is 21 and from here to here is 8. I know that from here to here is 9 and from here to here is A. But that tells me that this whole segment here is equal to 9 plus A. So I know that the outside times the whole thing is equal to the outside times the whole thing. 8 times 21 is equal to 9 times 9 plus A. Multiplied here and got 168. Used the distributive property here and got 81 plus 9A. Subtracted 81 from both sides and got 87 is equal to 9A. Then tried to add one more line here at the bottom and didn't have enough room. So I'm moving over here. If I divide both sides by 9, I get 87 over 9 is equal to A. And I'm done. That's all you have to do. What I've drawn on this circle here, right, on the left side on the bottom, is a central angle. Right? A central angle. Okay, so two things that are going on here. I've got this central angle that is a central angle because it has the center of the circle as a vertex. Okay. And then this arc here that is between the intersections of the circle and the angle right here is called an intercepted arc. Okay, that's what it's called. Now, we have talked about arc length before, okay? But what I want to show you here is that this arc, whatever its length is, has something called an arc measure. And this arc measure is going to be defined as the same as whatever this central angle is. So the arc measure equals the central angle. An inscribed angle has its vertex on the circle. So an example of an inscribed angle that intercepts the same arc as the one I just drew, and this is sort of random, I'm going to pick any point on the circle, any point at all, and make the arc that is inscribed and intercepts the same arc. That would be here and here. Okay. The measure of this angle here is half of the measure of the arc. And it doesn't matter where I draw it. You do not have to draw all of these on yours. I'm going to draw a bunch on mine. I think if you drew it on yours, it would be complicated more than it needs to be. But if you pick any other point from here to here, say, and from here to here, vertex here on the circle intercepts the same arc, this angle has to have the same measure as this one, 1/2 of theta degrees, because theta is the measure of the arc. Now, if you think about it, if I were to extend this out, and you don't have to draw this either, just notice it. If I extended this out, the central angle, and made it into chords instead of just an angle, look at what would happen. This and this would be vertical angles, right? So they would be equal. And then this would still be a central angle, so this arc would be equal to this arc. And it would be equal to this angle. Okay. So let's look at what happens if I draw two chords that don't intersect in the center, but they do intersect inside the circle. Okay. So let's call this angle A. Okay. And say that this is A degrees right here. And this is going to be A degrees too. But you can tell, if it's not at the center, these two arcs aren't the same length. They're not the same arc. They don't have the same arc measure. What we know about these two arcs, though, as you move this away from the center, the measure of these two arcs average out to the measure of this angle here. In other words, if this arc is B degrees and this arc is C degrees, then A degrees is equal to the two of them added together divided by 2. Yeah?
So would A always be congruent to angle measure?
These two?
Yeah.
They're vertical angles. They're always congruent. Notice, by the way, that's not different from this. If you look at the measure of the arc here, if this intercepts this arc here, but the vertex is at the circle here, there's no arc here. So if you add 0 and theta and divide by 2, you'll get the measure of this arc, which is theta divided by 2. So it's actually the same. This is the rule that applies to all of them. Yes?
What is theta?
Theta is a Greek letter that we use to as a variable to measure angles, usually. So instead of putting x there, I put theta. So this is what happens if you have an inscribed angle intercepting the same arc. Here's what happens if you have two chords that don't cross in the center, this is the relationship between the arc measures and the angle measure. The only other situation we can have is where we have two tangents or secants or anything else that intersect outside the circle. Okay? And if I have two that intersect outside the circle, I've got an arc measure for this, which is pretty big, an arc measure for this, which is smaller, and an angle measure here. Here's the deal. Over here, if they intersect inside the circle, you add them together and divide by 2. You add the two arcs together and divide by 2. If the two lines intersect outside the circle, you subtract the arc measures and divide by 2. C here is going to equal A degrees minus B degrees divided by 2. And you might, I don't know if this will help you or make it more complicated for you, I would write myself a note that says inside, add, outside, subtract.
You have two arcs and the outside of them?
Right, don't I? I have one here and one here. Yeah.
So the one you were doing before this, what do you mean the inscribed angle intersects the same arc?
You mean way over here?
Yeah.
Okay. This is the central angle, right? And it creates this arc because that's where the angle and the circle intersect, right? This arc measure gets its measurement from this central angle. An inscribed angle is one that has its vertex on the circle. If it intercepts the same arc, it means that when it crosses out of the circle, it's hitting the same arc here as this angle did from the center. So this angle and this angle intercept the same arc.
So does that mean they're the same angle measurement?
Well, not in this case. And what we just said here is that the inscribed angle that intercepts the same arc as the central angle has a measure of 1/2 the arc measure.
That for an inscribed angle, it doesn't always have to intersect the same arc as the central angle?
It will always intercept an angle that has a central angle. So in other words, let's just quickly sketch this, right? And this is why I don't draw. If I take this, and this is my inscribed angle, right? This arc measure here, whatever this is, gets its measurement from the central angle that creates it, right? Well, now, this inscribed angle intercepts the same arc as this particular central angle. So whatever this measurement is the same by definition, and this has to be half. One last little thing, because I only have one circle left anyway, and that is, what if I have a tangent line and a secant line? So I have an angle measurement here, right, which we can call x degrees, and I have an arc measurement here, which we can call y degrees. But you notice, like over here, I had 2 to subtract. Here I don't have 2 to subtract, I just have 1. Or if you want to think of it the other way, I have one that's y degrees, and the other one, because it's inscribed, is 0. But basically, x is going to equal y over 2.